Can everyone hear me? Is this working? Okay. How about now? Can people hear me? Okay. There we go. Great. Okay, so we still have people joining in, so we wait 1 or 2 more minutes. I still see people at the door. Yeah. A couple people asked me about the same thing just a few minutes ago. The version of the of IPython that we are using is 3, and the notebook companion that comes with it. So your tree view should basically look like that. The project has now morphed into something called Jupyter. So that's how you can tell if you're running the right version. Once again, if for some reason you can't get this version installed and it's not working, I'm going to describe in just a couple minutes a fallback plan that we have to get you up and running on a hosted setup. Okay? All right. So first of all, welcome everyone. We're thrilled to be here for the 3rd edition of Hands-On with Pydata, how to build a minimal recommendation engine. I'm joined by Vahid. My name is Diego, both of us from Unada. We are a startup in Toronto. And I was hoping Vahid would say a few words about what we do real quick so that you know why it is that Python is an integral part of our stack and what it is that we do with reco engines. Okay? Thanks for that. So the first thing that I think we should do is go through the environment check and make sure that everyone's got the data files, everyone's got the notebook, and everyone is following along. So there's 2 setups. There's a primary and preferred method, and there's a fallback option. So the local setup is the preferred setup. The instructions are on the link that we had up before a few minutes ago. So can I get a show of hands for people that were able to successfully load the setup locally and are running IPython? Okay, most of you. Okay, great. So what I'll ask the other people to do is to sit next to someone that has that setup. Okay? So if you couldn't get it on your local machine for some reason, then I'll ask that you so can I get a show of hands for the people that didn't get the setup running locally? So only one? Okay, one here in the back as well. Okay, keep the hands up for just a couple more seconds. Okay. Yeah, so I'll ask that we pair up. And now what I'll do is I'll describe the fallback option, which is a hosted setup with a little project that Zach Howard, one of our engineers, started working on that's called IPython. So for the people that didn't get the local setup working, go ahead and point your browser to this URL. It's right here. pycon.unada.com. And you will see a text box, a single field there for a username. Okay, so it's pycon.unada.com. If you Yeah, so go ahead and pick a username, just your first name, something. This is a bit of a fragile system that we put together as a fallback option for the tutorial. Go ahead and enter your first name without any weird characters or spaces or anything like that. And what that'll do is it'll drop you into a tree view that kind of looks like this. And that will be your own hosted setup on the cloud that we put together for you. It has the right versions of the packages. It has everything. So you should be able to be fine with that. Now, the reason why we want this to be a fallback option is because it's a single instance that we're running on AWS. So it could be a bit fragile if we get all the 50 attendees on there. Okay. So once you're there, you can go ahead and click into the PyCon IPython file or notebook, and that'll drop you into the main file, which is what we're going through right now. So is everyone seeing the same thing right now on their screens? Yes? Okay. All right, great. So just a little bit about this tutorial, what we're going to do, the roadmap that we're going to cover, the agenda, and then I'll take any questions as you will, and feel free to interrupt at any point. First of all, in terms of the references for the literature that we use to put this together, please check the list at the bottom of the notebook. There's some great books there and papers from the recommendation literature that I highly encourage you to check out. The data set that we're going to use is the movie lens from Group Lens Research, from the Group Lens Research Group. This is a 1 million data set. It contains ratings collected from about 6,000 users on 4,000 movies. And we ask for a special permission from the Group Lens group to use this data set for this tutorial. The only request from them is that you don't share this for any kind of commercial purpose, or that you don't put it up on another website of your own to share limitlessly in any way, okay? So only for the purposes of this tutorial. So really the goal of the tutorial is to provide you with a hands-on overview of these two main libraries from the Python scientific community, NumPy and pandas. We have decided, based on some feedback from last year and some decisions that we made recently, to leave PyTables as a bonus section if we have time, as an aside. And hopefully you all agree that that's the better approach as we go through the tutorial. And of course, we're not going to go through an exhaustive overview of the recommendation literature. That's an entire field of its own. But mostly what we're going to do is we're going to use the recommendation problem as a motivating example and a common thread to take us through some of the more common functionality of these libraries of NumPy and pandas. And of course, I don't think that we're going to crack the next Netflix or Kaggle in this tutorial, but hopefully it'll be the start of something that you can build on your own. So once again, incorporating some of the feedback from last year, one of the things that we're going to try to do this time around is to switch often between theory and practice, okay? And for that, I would like everyone to make sure that you can also load the questions notebook. Also within your tree view, there's two IPython files. One of them is called PyCon, and the other one is called questions. We're going to be switching back and forth using these two notebooks as we go from the theory to the practice, so that you guys can try things out, okay? So can everyone access that questions notebook as well? Can you see that? Can you load it? Does it work? Okay. I can definitely tell that this is the first tutorial after lunch, but we'll fight through it. Okay, so here's a quick overview. What we're going to do is we're going to introduce the theory of the recommendation problem from a computer science standpoint, kind of like to motivate what it is that we're trying to solve. We're going to learn about the Panda series and the data frames. So that's going to be more of a practice going into the notebooks. And then we'll go back to the theory to see some known solutions and challenges of the recommendation problem. We'll then load the data and set up some little machinery that we're going to need to test the different solutions that we're going to come up with. And from then on, we're going to iterate through a few versions, version 1.0, 1.1, and so on, of minimal recommendation engines. Now, The idea is that as we go through these versions, we're going to guide you through a few that we've put together ourselves. But very often, we'll be switching to the questions notebook so that you can write solutions of your own. Okay? And the machinery that we'll set up for evaluation will allow everyone to compare their solutions. So we'll have a standard way to know how performance stacks against, or between the different solutions that we come up with. Okay? Any questions so far? No? Okay, cool. And so the challenge piece, which is all the way at the end, is something that we're going to try to get into as we start going through version 1 and 1.1 of the recommendation engine. Because the idea is that towards the end, if we have time after the break and after we get some coffee, that's really needed, as I can tell, the idea is that we're going to have a bit of a leaderboard where people will post their different scores from the solutions they come up with. Okay, so we're going to do a bit of a mini Netflix challenge with minimal recommendation engines as well, very minimal. Okay? All right, so let's get started with a little bit of the theory about the recommendation problem. And, nothing new here. Recommenders have been around since at least the 90s. Today we see very different flavors of recommenders all around the web. They're deployed across different verticals. So companies like the ones that you for sure have heard of, Amazon, Netflix, Facebook, Last.fm, and so on and so forth. But what exactly is it that they do? I've pulled out a few definitions from famous papers from the literature, so I'm just going to read through these. Here's one from Resnick and Varian, arguably the people that coined the term, or maybe Goldberg. In a typical recommender system, people provide recommendations as inputs, and the system then aggregates those and directs them to the appropriate recipients. Collaborative filtering, actually this term was coined in this paper as part of a system called Tapestry. Collaborative filtering simply means that people collaborate to help one another perform filtering by recording their reactions to documents that they read. So this is in the context of that Tapestry system, and it was about recommending documents. Here's another one, a more recent one from 2005. In its most common formulation, the recommendation problem is reduced to the problem of estimating ratings for the items that have not been seen by a user. So this is the critical part, right? It's the set of items out there in the universe that you still haven't interacted with or still haven't rated if you're thinking about Netflix, for example. So intuitively, the estimation is usually based on the ratings given by this user to other items and also on some other information. Once we can estimate ratings for the yet unrated items, we can recommend to the user the items with the highest estimated ratings and so on and so forth. And then one from 2012, driven by computer algorithms, recommenders help consumers by selecting products they will probably like and might buy based on their browsing, their searchings, the purchases and preferences. So you can see how the definitions are also touching upon the different data sets that you could use to build a recommendation engine, the different data sets that you could tap into, where there's more implicit feedback or more implicit signals like navigation patterns, for example, as this paper is saying, and the more explicit feedback like actual ratings or reviews from a user base. So this, I promise that the math part is very short, and we'll very quickly jump into pandas, series, and data frames. But let's do this real quick so that we're all on the same page about what the problem is. So we'll set up some quick notation. Capital U will be the set of users in our domain, and the size, the number of users in our domain will be denoted with the vertical bars around capital U. In the same way, I will be for items, and we'll use the modulo for the number of items in our domain. I of U will be the set of items that a user has rated, and minus that will be the complement, so the things not yet seen or rated by the user. And in the same way, U of I will be the set of users that have rated an item, and the complement will put a minus sign in front of that. S of UI will be a utility function that measures the utility of an item for a user. So that's kind of like the metric that we're trying to optimize. So really, when you think about it in this way and you express it with this notation, the goal of the recommendation system can be very simply expressed as finding that, that item from the set of items that the user hasn't yet seen from -I that maximizes that notion of utility. So we're trying to find out of the universe the things that you haven't seen, the first or the second or the top K, typically the top K, items that maximize this notion of utility. And as in most of computer science, is something that I always say because I think it's fascinating. As with most of computer science, it's very easy to state the problem. Solving it is a different thing, but it's very easy to state the problem. And so think about this. In its most basic form, if we have a matrix where we have users arranged along the rows and we have items or movies in this case arranged along the columns, then typically you'll have some ratings that tell you that, for example, user 6 rated movie 1 as a 2-star or user 1 rated movie 3 as a 4-star. But the vast majority of the numbers or the cells inside this matrix will be question marks because it's a sparse scenario. Not everyone has seen everything, right? Obviously. And so given this partially filled matrix of ratings, which has this size, usually very large, the recommendation problem is to simply estimate the missing values. Fill up the matrix. Okay? That's it. That's as simple as it gets in terms of defining the problem. Did everybody follow me there? Does that make sense? Okay. Yeah, questions, please.
I guess you're making, is there the assumption that if they have not rated a movie, they have not seen it? So somebody may or may not actually.
Yeah, so so the question is the assumption that if the rating is not there, it means that they haven't seen it? I think that for the purposes of the work that we're going to do here, the answer is yes. Whether we can, I think that the key in coming up with ideas to handle those scenarios is using the other more implicit signals that we were talking about that are outside this ratings matrix. But yes, that was a very good question. Okay, so let's dive into a little bit of practice. Let's look into pandas, Python data analysis library. So a bit of an introduction with a few words from the author of this library. So Python has long been great for data munging and preparation, but less so for analysis and modeling. And pandas helps fill this gap, enabling you to carry your entire data analysis workflow in Python, because Python, as you know, is a very general purpose language, without having to switch to a more domain-specific language like R. And so the idea is not that people that are big fans of R are going to hate on pandas or the other way around. I think that, in fact, pandas is very much inspired by R and by its data frame object. So you could think of them as complementary, but the goal of this library is exactly to bridge that gap so that if the rest of your application is already in Python, then you can, in the same language, use a tool that allows you to do a lot of modeling and data analysis. Okay? So at the really heart of the pandas library is an object called the data frame for data manipulation. And my preferred way to think about the data frame is just a good old spreadsheet. Okay? A spreadsheet that has labels along the rows and labels along the columns. And you can do a lot of things with it. It features a very powerful index object, data alignment functionality, handling of missing data, something very critical in the real world when you're loading data, and we'll see that here. Aggregation with group by, something that we're going to work on quite a bit, and data manipulation via reshape and pivot and some other functions like slicing and merges. Okay? So we're going to get started. The first thing that we're going to do is we're going to use some conventional notation to load NumPy and pandas. NP and PD is usually the norm, but it's not required. And then here's just a few print options that are not really interesting. So I'm going to skip ahead. And what we'll do is we'll go through the basic functionality of the series and the data frame, and then we'll switch over to the questions notebook, and we'll have a few questions for you to fill out on your own, and we'll give you a few minutes. Any questions so far? Is everything making sense up to here? Okay. So the series object is a labeled array. It's kind of like an ND array from Python. It actually used to be a subclass of that historically that supports more meaningful indices. So you can easily construct a series by using the series constructor, the basic initializer, and you can pass in a list of floats, for example. And so that'll give you something that looks like this, and you'll see that there's a default index that's created for you that goes from 0 to the length minus 1 of the list that you passed in. So you can see that my 2.0 is here, 1, 5, the values that I've passed in are on the right-hand side, and pandas is creating a default index for me. Now, of course, this is not really the most interesting case for using a series. The power of the series is that you can use more meaningful labels for your index. And so, for example, here, I'm using the more complete version of the constructor where I'm passing in a data keyword argument and an index keyword argument. And so that'll give me essentially the same series, but now my index potentially has some meaning for me. And so in the context of what we're going to be working on today, if we express a movie rating instance as a dictionary, as a Python dictionary, you could easily pass that into the series constructor, and you get a much more meaningful index object now with the different values. Okay? And so you can access these two properties that we've been referring to using dot notation. So the series ser, which is what we're using to name the object here, has a dot index property and a dot values property. And the index is an index object from the pandas library, and the values is just a NumPy array. Okay? In order to index into the series, there's a few different methods, and this has changed over the versions with pandas. So this is something that I'd like everyone to really pay attention, because it'll be critical when we build and use some of the real data sets that we're going to work with, or the real data set, when we build our minimal reco engine. So .loc allows you to index into the series using label-based indices. So for example, if I have a series that looks like this dictionary that we were just presenting here, then in order to get to the value that belongs to the gender element of the index, then I can just use LOC and using dictionary notation pass in the label that I'm interested in retrieving. And so that comes back with an F. Okay? In the same way, I can also pass in a list of labels to get many of them at the same time. And what I actually end up getting is another series with 2 elements. You can also use Boolean-based indexing using the same .loc method. And basically, wherever you pass a true value, that element will get selected, and wherever you pass a false, that'll get ignored. So in this case, if I'm passing all false and only one true value here, as you can see, then I'm retrieving the rating object. And we'll see where this makes sense as we build the reco engines, but Boolean indexing is actually very useful. Yeah, there's a question back there.
You may have mentioned this, but if the series had multiple movie ratings in it, and I did series dot load gender, will I get a series of gender?
We'll try that in the questions. Yes. I actually believe that there's support for duplicate elements in the index. We won't have to worry about that in our setup, but that's kind of the goal of the questions. We're going to play around with some other ideas. And okay, so that's as far as label-based indexing is concerned. There's a counterpart method called iloc, that allows you to index based on positions, so integer positions. So if you wanted to say, I just want the first element of this series or the second element of this series, then you can use the iloc method. Okay? That also can take a list of locations, and basically that gives you the first and the second, for example, element of the series. And finally, there's the ix method. That's arguably the most flexible way to index into a series. Because it knows how to fall back from one to the other. It knows how to handle the two. It knows how to handle integer-based locations and also label-based. And we'll see that IX is very useful for data frames when we want to pass some slices in and get a subsection of the data frame. Any questions so far? Now, what's really critical about having this index object is that once you start operating between different series, then the operations will take the index into account, and it'll not mix and match. Yeah?
Just jumping back,
Yeah.
when you use the IX, where you directly array reference it, is that
That is equivalent to the IX. Yes. Yeah, so the question was over here where we are just passing some list of locations without using IX at all. And so what's critical, as I was saying, is that these index objects really play an important role in the operation. So for example, if I have two series with different indices and I decide to add them together, then pandas will automatically align those two and give me the right answer as I expect it to be. In the sense that if B doesn't have a counterpart on series 2 to add it with, then I'm going to get not a number. There's different ways to configure the behavior when this happens. I could, for example, decide to ignore the NANs, or I could, for example, fill the NANs with zeros, things like that. But at least I'm not going to get cross-label noise, if you will, with numbers or a sum that wouldn't make sense. So if you're adding A's and G's or apples and oranges, then it wouldn't make much sense. Okay? And the other critical part about the index is that it'll also, in the process of aligning when you're doing operations between series, it'll also know what to do in terms of the different types. So for example, going back to the same case back here, if the series happen to be of different types, there's a D-type keyword arg that you can pass in, then pandas will do automatic upcasting for us when we operate them together. Okay? All right, let's look at the data frame before we jump into the questions. I think it's important to see the two together because I like to think of the data frame as just the two-dimensional version of the series. You could think, as we were saying before, you could think of the data frame as this spreadsheet that either is a collection of series that represent the rows of the spreadsheet or a collection of series that represent the columns of the spreadsheet. And so here's an example for how to construct a data frame from scratch. So you use the data frame object. And into that init function, you can pass in, for example, a dictionary with lists of numbers. So here, if I say column 1 contains these 3 floats, and column 2 contains these other 3 floats, then I get back, the notebook is formatting this into HTML for me, then I get back this data frame with the automatically created index from 0 to 3, and I have 2 columns according to the labels of the dictionary that I passed in. Does that make sense? Now, I can be, again, more explicit about the columns that I want, the column names that I want, or the index names that I want. If I pass in the columns keyword argument with column 1, 2, and 3, then Pandas is even smart enough to know that there was no data for column 3, so it's just a bunch of NANs, right? And if I use the index keyword argument, then I can pass in the names of the observations, for example. And now I have a fully specified spreadsheet with meaningful labels along the rows and along the columns. Okay? So just some more variations here. You could also think of that as a dictionary of series. There's many variations to construct it. And the columns and the index of a data frame can also receive they also expose a .name property that allows you to give some more semantics or give some more context as to what the columns or what the rows represent. All right? So in this case, I'm even labeling that as well. Okay? There's a .t method that allows you to transpose. And this is how you access the columns and the index and the value. Okay? So something that is important to also pay attention here is how to delete and add entries. There's a drop method for the data frame that takes the name of a label and allows you to get rid of whatever you don't want. And you can also, by passing in an axis keyword argument, you can indicate whether you want to drop a row or a column from the data frame. Okay? And you can very simply add new columns using dictionary notation. So if we have a data frame without R3 as a rating, then you can very easily, as long as you pass in the right number of objects and in the right order, you can use dictionary notation to create a new one. And it could also be a series. So in this case, I'm passing in a list, and in this case, I'm passing in a series. Okay? So what we're going to do is we're going to give you a couple minutes, and I'm going to ask you to go to the questions notebook, where you'll find a section called Pandas Questions, Series and Data Frames. Okay? and we'll give you just a few minutes to fill that out. It should be very, very simple. Okay, so what I'm going to do is I'm just going to pick someone random from the audience and try to get an answer for the first one. So, gentleman here on the far right. So number 1 says, adding a column in a data frame. So given that data frame, how can you add a new column to it?
I have the column, set on the name of the column.
Okay, so just passing it into here. So yeah, so that's one option. I can modify the actual constructor and in one go add, for example, a column 2 here and then pass in another list. Now, what if all I have is access to this object? How do I modify that? Yes? Okay. So I can set it like in a dictionary. So I can use dictionary notation like that and for example, say my new column and then set that to I'll just copy paste the same values here.
The only way you can make that larger is very tiny.
Yes. Is that better? Okay. How about the people in the back? Can they see anything at all? Okay. Is that better?
Yeah.
All right. So as we heard from the back, using dictionary notation, so if I have the object already, it has column 1 as we print it out here. Now I'm going to execute this cell again. Oh, and I never imported, so I got to do that first and then execute that. Okay, so we see now we have the original column that we passed in with the dictionary when we created the data frame, and now a newly created column with this label. Make sense to everyone? Fairly simple? All right. So for number 2, someone from this side. No one's looking up. How about yourself? Yes? Okay, so the question is, how do we delete a row in a data frame? Okay, so this is what we have. This is what it looks like. And I heard df.drop. So just to show you guys, in case you're not familiar with the notebook, so the first thing I'm going to do is I'm just going to run this here. If you know that drop is the name of the command or the method that you want to use, the notebook will allow you to say question mark like that. And then if you run this cell, you'll automatically receive a doc string from the bottom popping up. And that'll tell you how to use that method. Okay, that's pretty cool. So if I forget, for example, that drop takes a label, then this piece of documentation here will tell me that. Okay. So then if this is my data frame, I'm going to print it out once more. I'm going to get rid of this here. Okay. Then if I say drop row D from it, that's what the question is asking for, then that's how we do that. Okay, yes, question.
If you print later,
I'm sorry?
if you print the PDF, then
Yes,
you have that
great
draft
question.
you assigned.
Great question. So the question
Try to
was,
figure out what I was doing wrong.
what happens if I print df again here? Okay? So what happens is I didn't delete it. The reason for that is that this here actually returns a new object, a new data frame object. Now, what that means is that Pandas is falling back on the safe side and saying, I'm just going to give you a new object instead of modifying the one that you have. Now, if you're absolutely sure that you want to do this as an in-place operation, then it couldn't be easier than saying that. In place equals true. Okay? And I believe that that still works in this version. That should do it in place. All right? Yes? Well, I think that's just a matter of taste. Maybe there's some memory differences if you were to dig into the inner workings of the library. If you were dealing with very, very large objects, then I think that would have an impact. Otherwise, probably not so much.
Or do you suppose they made the default behavior not in place? Because it seems like the notation suggests that.
Yeah, so I think this is a common theme, and I've seen this in NumPy as well. And it has to do, it's a number of things, but I really think it has to do with falling back on the safe side of, if that's your object that you're working from, then exactly. I think non-destructive is the best way to describe it. But that's all I can say about that. May not be the most satisfactory answer. Sorry?
It's very functional, stateless in the sense that like
That's right.
you can do things distributed that way.
Mm-hmm. That's right. So the comment, I don't know if everyone heard, but the comment was that it's more functional in that way. Functional being that you're passing data through functions, right? And you're not modifying the state of the objects, but you're only streaming data as inputs and outputs, right? Yes, question or comment? Yeah. Sorry, I clicked. Yes, correct. So you have to make sure you have enough memory to do that because it is returning and creating a new object. So that's a very good point. If you're working with very large data frames, you have to be careful there. All right. Number 3, question number 3. Someone from the back row, back there, all the way to the back row, far right. Can I get an answer for number 3? So creating a data frame from a few series. You pass in a dictionary, okay? So something I could do is, if I want my data frame to hold this series as the columns, then I could use the labels as the keys of my dictionary. Correct? Was that the intended answer? And then the series objects as the values. Okay? So I'll just do 2, or we'll do them all. Number 2 and 3. Number 3. Okay? Did that make sense to everyone? Yes.
So I did this well for this one. I just added the series in a list, and then each one of them became a row.
Okay.
So I wonder, with pandas, there seem to be so many ways, so many entry points. What are some of the useful intuitions that you've developed over time about how these things are organized?
Yeah. Usually, as we'll do today, you are creating data frames out of CSV files. And we'll see that there's a dedicated function to do that. So I think that'll help you with that. In my case, I'll usually try. I think there's a from records. I think for the most part, in my case, I'm using this dictionary notation as it looks like, as you see right here. But when you're loading, the reason I mentioned the CSV case is because when you're doing that, there's more optimizations built into that function. And we'll see how to do that and how to put them together if you're loading data from many different files. Any other questions or comments? Okay, cool. So we've successfully completed the first portion of the questions notebook. what we're going to do now is we're going to go back to some of the pandas series and data frames fundamentals, and we're going to talk about indexing. Indexing is one of the key pieces of functionality that we want to get a good grasp of before we dive into the recommendation problem. So data frame indexing. You can indexing to a column using the label with very simple dot notation. Okay, so provided that it doesn't start with a number and some other things that might be limitations from the Python side. If I have a data frame, for example, that looks like this with observation 1, 2, 3 as the rows and columns 1, 2, 3 as the columns, then I could use dictionary notation like that to access that column, or I could also use dot notation like that to access it. Maybe that's better. Okay? And once again, like we were doing for the series object, you can also pass in a list of labels, and that'll simply get a subset of the columns that the subset of the columns that you're asking for. The data frame has counterpart .loc and .iloc methods that allow you to be explicit about whether you want to index using labels or whether you want to index using integer positions. And maybe I didn't mention this at the beginning, and I should have. Maybe you're wondering why the different functions, why do you even care? So the reason for that is that you don't always have clarity between which of the two you want to use, and that's why these methods are there. Sometimes your natural labels could actually be integer numbers. So if you pass an integer, there's no way for pandas to know whether you want that position or if you want that actual label. So that's why there's the breakdown of the functions into these explicit categories. Okay? And then once again, the IX method is arguably the one that gives you the most flexibility when you want to do more fancy indexing or slices into the data frame. So here you can pass in a label or a position, and you can also pass in a range. You've probably seen this from standard Python lists that you can use the colon notation and say, I want the first 2 elements, for example. And that'll give you the first 2 rows of the data frame. IX can also take both columns and rows specifiers into that method. And so here, for example, you're saying, out of the first 2 rows, I'm only interested in the first column. And so that's a subset of the data frame. Okay? Questions about that? All right. So once again, let's quickly switch over to the pandas questions on indexing, and we'll give you guys 5 minutes or so to go through those. I think they're actually very simple. So go ahead. These are quite simple. So how about someone from the first row here? Could I get an answer for number 1, indexing into a specific column?
If you, I have df.column_2.
Okay, so this is using dot notation. Okay, and that'll work just fine. That comes back. So what is the return value of this? What am I looking at here? Exactly. That's a pandas series, right? It's a single row or column of the data frame. All right. for number 2, for label-based indexing, maybe someone from, again, the last row of the right-hand side. Anybody? Or yeah, okay. Or this side. Go ahead. Go ahead. Yeah. Yeah. Yep. Okay. Observation number 3. Okay. Did that make sense to everyone? Fairly simple. We're using the IX method. What's another way in which we could have done this one?
A double bracket with would be the index number, or if you know what number the column is, you could just enter the number of the column.
That's right. And so if it's based on labels, the other method that we can use is LOC, right? But I don't know if that'll work for the row. Yeah. Did it do it? Yeah. It did. Okay. All right. And last one for number 2, position-based indexing. Anybody? Yourself? Yeah? So, okay, so if it's the first row, that should be a 0. Okay. So again, in this case, since we have a clear distinction between integers for positions, and in this case our labels are strings, we're calling them names like observation 3 or column 1, IX can handle that very easily. Okay. But if we wanted to be explicit about position-based indexing in question number 2, the other method that we could have used is the iloc. Okay, the iloc method. Okay, great. So we'll just leave this here. We'll come back to that later. Any questions so far about pandas, about the series objects, about the data frames, anything at all? Okay. Those are always good ideas, but those are more on the control of the application developer. What Pandas does for you is give you that ability to use the iloc or lock methods so that it knows what you're talking about, so to speak. That's kind of the mechanism. I've actually ran into many situations where there's ambiguity and sometimes you don't even know what's going on. So in older versions, iloc and lock didn't exist. So sometimes there's no error visible to the user, but you're getting the wrong pieces of the data frame. So this is very useful. All right, so I'm going to talk through a little bit of the process that we're going to go through using the read table functions that we were just discussing as this question came up to load the .dat files from the movie lens data set. These are just text files. You could think of them as CSVs. It's just that the separators are a little different. For the people that are running on the hosted solution, I ask you to hold off on running these commands because these load the full 1 million data set into the box. And you're not even going to need that for the purposes of this tutorial. There's a pre-selected set of ratings that we've separated into training and test, and they're much smaller, so you'll be able to work with that. So we'll get to that in a moment, but I just want to showcase some of the capabilities of Pandas to work with real data, to load data from files. So here we're using the read table function. I'm just going to focus here on this cell. The movie lens data set is broken up into three main files: users, ratings, and movies. Okay, it's kind of normalized in that way. The separator is the double colon here. And so you can see that read table takes a very large number of keyword arguments. So you can customize the separator that you want to use. Are you going to ignore a header, or are you going to actually read it? What are the names of the fields that you want to use for the different columns and so on? And so here what we're doing is we're loading 3 different data frames. One will be called users, another one will be called ratings, another one will be called movies. And we're using the head function here, the head method of the data frame, to take a look at the first few rows. This is always something that's very useful if you're familiar with the Unix set command, for example, that's very useful when you're working with very large files. You don't want to quite open them in an editor or something like that. You just want to take a peek at what's in there, get the first few rows. This is also very helpful when you're working with the notebook so that you don't pollute your notebook or your working environment with thousands, if not millions of rows. So that'll give you the first few. Was there a question there? Yeah.
Yeah, Jack, depending which version of Python or stuff that put into this Python to get to look like.
Yes, and I did get a warning about that in the other notebook. Yes. So was that in the PD? Was that in the PD read function?
Yeah, all three of the read functions need engine equals Python if you're running
Okay.
whatever it is I'm running, it's just the combo.
Okay. So for everyone to see, that would be a keyword argument here. Engine equals like that.
Mine didn't give results.
Oh, really? Okay. Well, so it's good to know then. Thanks for bringing that up. In my case, I think it was also a warning. So any questions so far? We're only taking a look at the ratings file here. You could just as well decide to have a look at the first few rows of the other two. But basically what you're getting is this kind of record file that identifies each of the rating events. So each rating event is going to have a user ID, a movie ID, the actual rating, a timestamp, and some other information about the users in the movie. Okay? So next, we're going to use the PD merge function twice to merge all of these files into one. For the people that are familiar with SQL, what this is doing is a bit of a join of across all the files based on the IDs. Pandas is very smart about that as well. And it allows you to merge it all together into a single data frame. So once we load all of that and merge it all into a single one, here's what the full record looks like. So this is the first few rows of that movie lens data frame. Okay, so you can see that there's information about the user in terms of gender, in terms of age, in terms of their occupation with an integer code, a zip code. There's also the title of the movie and so on and so forth. Okay? Yes? I'm sorry? Yes, exactly. It's kind of like a SQL join. And I encourage everyone to do this in your, so I'm just going to add a cell here just so that I show you what I mean. I encourage everyone to do one of these to really see the breadth of keyword arguments that this function can take so that you can understand how to control that. Because you can also, for example, pass in a specifier for how you want the join to be. Okay, if you don't have, I don't know if you're familiar with SQL, but you can also specify inner or outer if you don't have a record on the other side, and so on. Okay? Any other questions about that? Okay, so the next thing, I'm just going to go very quickly through this because I think it's only important that you get the gist of what's happening because it'll help us evaluate different functions for the little recommender systems that we're going to build. But you don't really have to understand every detail of what's going on. So before we start building our minimal reco engine, we need a mechanism to be able to compare your reco engine with somebody else's. Is it better? Is it worse? How does it perform? And so on. And so for that, we're going to do a few things. We're going to split the data into training and test sets. We're going to introduce a performance criterion, and we're going to write an evaluate function. Okay? So the idea of training and test is that we're going to take the entire data set from Movie Lens, and we're going to pretend that there's a portion of that data that we haven't seen, that we don't know, that we don't have access to. This is standard practice in the machine learning community. So what we're going to do is we're going to take the other portion, say it's a fifth and fourth-fifth or whatever kind of split that you want. We're going to take the other larger portion and we're going to build and train a recommendation engine on that. And then once we're happy with how we're performing there, we're going to evaluate it on this held out data set. And based on the performance on that held out data set or the test set, we're going to compare the different solutions that we come up with. Okay? So here's a little bit of code to split that data set. You know, some of the challenges here is we got to take a smaller sample from the full million data set. Make sure that we also have at least a couple ratings per user in the subset so that they can be There's no edge cases to worry about. And then we're going to split that result into training and test. We're going to use some random functions. So there's no need to worry about what is going on here. I'm just using a few pandas built-in functions like value counts, and I'm also going to use some NumPy functions like random choice here to be able to say which row of the large file goes into training and which one goes into testing. Okay? So this is just there for completeness sake, and you can go back. I encourage you to go back and look at how these files are created. Okay? So out of this process, I generated, before the tutorial, I generated 2 files under your data directory. So make sure that you have that. One of them is called movielens_train.csv, and the other one's called movielens_test.csv. The reason why these here are prefixed with my generated is because if you happen to run these functions, you will overwrite the file. So I just want to make sure everyone's working with the same files. And then last but not least of this machinery that we're going to need to test our solutions is a performance criterion or an evaluation function to see how well we are doing on this test set. This is an entire field on its own as well, and we've decided to go with RMSE, with the RMSE criterion. This is what was used for the Netflix challenge, so we think it's a safe bet. And it's a very simple function. In fact, I just wanted to highlight, as you look at this function, as you look at the equation here, and you look at the actual function in Python, I just wanted to highlight the power of NumPy and how there's no loops here or anything like that. Vectorization is implicit. Vectorization is something that in the old version of the tutorial we used to cover more in depth. But I think seeing this is already enough indication of how powerful that can be and how expressive you can write a function like that. Okay? So basically all this is doing is computing the root mean squared error, basically, whereby the error is the difference between what your recommendation engine thinks the rating should be and what the actual rating is. That's why we are splitting into training and testing. So we're going to learn about the user and the movie and so on and so forth using the training set. And then we're going to ask a question, what do you think this user rated this movie? And then we're going to compare that to reality, and that'll give us a score. Okay? And then there's a little function here that's also part of the question notebook that allows you to run through an entire test batch and compute your overall RMSE for your recommendation engine. So let's quickly go to the questions notebook again. The mini challenge preparation, data loading and evaluation functions. Let's switch over to that. And these are the commands that you can safely execute. Again, the people running on the hosted solution might need to be a bit more patient as the data loads. So this is how you load the training and test subsets. So I go ahead and run these commands right now so that you have these 2 objects in your environment in memory. MovieLens train and MovieLens test. And again, we're using another version of a data loader here from pandas that's called readCSV. And you can see how you can tell it whether you want a specific column to be used as an index of the data frame. There's also parameters to control the headers and all that kind of stuff.
For anyone being dumb and trying some Python 3 like I am, you have to add encoding equals Latin 1. Encoding equals Latin 1 to this function? Okay, so for anyone using Python 3, which I shouldn't be doing.
but that's fair for people that are trying that out. Encoding equals Latin 1. Okay. Okay, so once you load these 2 files, you can take a look at what one of them looks like, or either or, using again this head command that'll give you a first few rows, a look of what's in there. Okay, so you see, for example, that that training data set looks exactly like the overall data set. It's just a smaller sample. And the same thing for the test data set. Okay, so intuitively, a rating for a movie by a user shouldn't be repeated in these files. It's either in one or the other. That's what the code that we reviewed before was making sure of. Okay? And then also go ahead and execute these few cells here to set up the compute RMSE function, to set up the evaluate function. And so the first thing that we're going to do, our version 0 of the recommendation engine is going to be that function there that outputs a 3. Okay, so if you want to know what the rating is for someone, you're just going to say give it an average. Okay, it's a solution. Even though you might think it's not very smart, it is still a solution from the definition perspective. So go ahead and load this function, and then try to see if you can execute this line that says the RMSE for my estimate function equals blah, blah, blah. And I just got a name error. Maybe I didn't move. Oh, okay, I didn't load it. So I got to go one by one. And you should do the same. So first of all, load. There's the warning. Take a look at the data. Compute RMSE, evaluate, and test a dummy solution. So the dummy solution should actually come back with an RMSE. And it's important for us to know what the baseline is, right? This kind of gives us an idea, because RMSE for our case will be between 0 if you're perfect, or something like 4, right? Because the greatest distance between the worst that you could possibly guess a rating is say that it was a 1, and indeed say you said it was a 5, your reco engine said it was a 5, and indeed it was a 1. So you have a delta of 4. So between 0 and 4. So this kind of gives you a baseline of what you can expect from a dummy solution. So intuitively, what we're going to work on from now on and on the second part of the tutorial should give us something better than that. We should strive for better than that. And better in the case of RMSE obviously means lower than this number. Okay? Is everyone on the same page? Can everyone see this output on their notebook? Okay. Was there a question?
I'm stuck. I'm working it out.
Okay. And can I get a show of hands for the number of people using the hosted setup? Okay, we can handle more people on the hosted setup, no problem. So if something isn't working and you don't want to waste time fiddling with your local environment, as long as it isn't all of you, then feel free to go to that website and you'll be able to use that system and follow along. Okay. Okay, so we're going to switch back now to the main notebook. And what we're going to do is go through a little bit more of the theory. We're going to go back to the theory. Now that we've loaded the data, we've done some exercises using series and data frames, we're going to go back to the theory to go back to this context of the problem that we're trying to solve before we think about how we want to use pandas to solve this problem in a more sophisticated way than the very simple myEstimate function that we started with. So that's our baseline. We already have something. Yeah?
So we got the root mean squared error of 1.23.
Yes.
But I don't really know. I mean, I'm guessing it's not great unless a lot of people rate their movie 3.
That's right.
So how do I know if I've done good? Do I just make the baseline and compare against that, or can I tell right away?
Exactly. I think that you also want to think about the effort that you put into building the solution. So this solution takes 0 seconds to build, right? What does it give you? What's the bang for the buck, right? Right. Well, but at least you know that if you were doing worse than this, you would be having a problem, right? So from an upper bounds perspective, this is a baseline. So that's why we call it a baseline or a lower bound, depending on how you want to think about it. But that's a good question, right? What is it that we want to strive for, right?
Turns out 4 is actually better.
I'm sorry?
Turns out 4 is better.
Oh, okay, great. So we're already testing a few things, right? That's the spirit of this tutorial. That's the spirit of this tutorial. And that's exactly what we want to give you lots of time for in the second half. We want to let you explore how you can get a better score and get some insights into why that's the case, right? Very much like what the real Netflix challenge was like. But what I would also encourage you to do is to have a look at the bottom for references, because depending on the evaluation criterion that you use, you get different insights into how different things work. And also, I think that reading through some of the papers, especially in the context of that very famous challenge, you can also get a feel for what is expected based very, very sophisticated solutions like the winning ones. Okay, how great can you be? It turns out you're never perfect, obviously, but just to get a better feel for that, I encourage you to check out those references. Okay, so let's go back to the theory a little bit and talk about some well-known solutions to the recommendation problem. So if you were to look at that, for example, Adamovich's 2005 reference that we pulled a quote from, you'll see that that's a great survey to start from, and this paper categorizes the different classes or families of solutions to the recommendation problem. And there's basically two big families. You'll read about this everywhere. One of them is called content-based filtering, and the other one is called collaborative-based filtering. Okay? The idea of content-based filtering is that you recommend based on the user's rating history. Okay? So you're recommending based on, you're looking at that user, you're looking at everything else that they have rated, and based on that knowledge or that domain of information, you're estimating a new rating. Okay? So what that means is that if you want to know what I would think about the new Fast and Furious movie, then you would ask me what I thought about other movies of similar genres or different genres, and so on and so forth. Okay? And so here, mathematically, the idea is that you're aggregating in some way, you're aggregating over the ratings for you're aggregating over the ratings that the user gave to other items. So to all the other items in the user's purchase history. So remember, I of u is every item that that user has seen or somehow interacted with or rated in one way. And so here's the simplest way in which you could possibly do that. Take the mean of the user's ratings. Okay, so if I want to know what you're going to rate the new Fast and Furious movie, then I'm going to look at your entire rating history, and I could compute the mean of that and feed that as my prediction. And that's a perfectly valid solution, and we're going to test how that fares. Okay? On the other hand, on the other side of the coin, there's collaborative-based filtering. And the idea here is that you recommend based on other users' rating histories. So other people. Okay? So again, going back to the example of this movie that I might have not seen, if you want to know, if you want to estimate how I might rate that, then you could ask other people that have seen the movie. Okay, so maybe you don't want to go by my history, my personal history, but you want to ask other people. Presumably people that are similar to me, for example. And so, again, in the most simple example, in the most simple case, I could aggregate over other people's ratings using something as simple as a mean function. Does that make sense? So if you go back to this original matrix that we had at the very beginning of the tutorial with users on the rows and movies on the columns, a content-based filter is taking the mean of each one of those rows, right? And a collaborative-based filter is taking the mean of each one of those columns. And if that didn't make sense, it doesn't matter. It's important that at least you understand what's written here. Yeah?
So for every other movie, I voted very differently from everyone else, which is just biased toward my own average more so because
Of course. And I want to, so the question is, what happens if I rate very differently from other, I'm very critical, for example, right? What happens then? So what I want to point out is that when I show you these two solutions, I'm just giving you examples of these two families. They are not the best examples, but they're examples, they're valid examples of these two families. We're going to try to work through exactly what you just described in the versions of the recommendations that we're going to build. Any other questions? Is the basic idea more or less clear? And so one of the very important things to note about these two families is that in the content-based world, in the content-based family of algorithms, your recommendation engine can also be looking at item-specific or movie-specific information. For example, I could be looking at the genres of the movies that I've seen and the ratings that I gave to those genres, or the cast of characters, right? Or the director, or the people behind the soundtrack, right? That's why it's called content-based, because it is domain-specific. On the other hand, when you look at collaborative filtering, you're looking at ratings of other users. you don't care if you're recommending flat screen TVs, groceries, or movies. And that's very powerful because it makes your system content agnostic. Okay? And obviously, based on that insight, the third family, or there's many other families, but one of the other big families is the world of hybrid solutions. How do you combine information from a content-based algorithm with information from a collaborative-based algorithm? Okay. Some of the challenges from a theoretical perspective in terms of coming up with a solution for the recommendation problem. If you think about content-based techniques, then the availability of item metadata is usually a critical point. In the case of what we do, for example, if we want to recommend elements from or items that are sold by a grocery store, then typically you don't always have a full data set with nutritional information for every item, with ingredient information for every item, with the country of origin, with what have you, right? Sometimes that data is very sparse and very lacking. And so working around that is one of the main challenges, okay? And then common to both worlds of content and collaborative-based filters, the new user problem and the new item problem, both underlying the sparsity or examples of the underlying sparsity problem, are related to things like if you're someone that just joined Netflix, right, or just joined any other system, we don't know anything about you. How can we come up with a recommendation? Or if a new movie comes out that nobody has seen yet, then what do we do about that, right? Those are kind of the main challenges. You'll hear about them you'll also hear about them in terms of the cold start problem or the cold, right? Any questions so far about that piece of the theory, so to speak? Okay, cool. So what we're going to do, what we're going to do before the break is go through the version 1.0 of our minimal reco engine, and then I'm going to ask you to build a counterpart to this 1.0 that hopefully will do better. Well, we'll see. And we'll do that before, and we'll do that, and then we'll go to the break. So here's our minimal reco engine v 1.0. And I see that everyone's super excited about this. You're holding it back. So what we're going to build is a content-based filter, okay? And we're going to go back to that very simple idea when we were going through the equations that we're simply going to aggregate the user's ratings using a mean aggregator, a mean function, okay? And this is how we're going to do it in pandas. We're going to define a function. It's going to be called content mean. And this is the signature that we're going to use for all our recommendation engines. It's going to be, whenever we build a reco engine, the contract that we're going to abide by is that it'll be a function, or in the class at least, there'll be a method that takes a user ID and a movie ID from the data set. And it has to return a single floating point value, which is the estimated rating, okay? That's the contract that we're going to abide by. So how do we do this? How do we build a content-based filter with mean ratings? If user ID is what I receive here in the function for movie ID, then the first thing I need to do is find all of the ratings for that user. And a way to do that is by using the Boolean expression that we assign into user condition that says, out of the user ID index, or user ID column, sorry, in movie lens train, I want all of those that are the same as the user ID you're passing into the function. And what that comes back with is a list or an object full of Booleans, okay? An index of Booleans. And this is why Boolean indexing was important at the beginning. Because we can take that user condition and pass it into the LOC method, right? The label-based method for indexing, and obtain all of the ratings for that user. We want to index into the rating column specifically, because we're not interested in other things like the timestamps of those ratings. We're interested in the actual rating value. And then Pandas provides, or a series, provides built-in methods like, for example, .mean. And that computes the average. Okay? Yes, questions about that?
Yeah, for
Overfitting?
If we use the test, like we don't
Oh.
generally don't want to use the test data, right?
Correct.
I understand that, but if all we're doing is taking a mean, I don't know if the same concerns apply.
Well, I don't know. We could have a chat about that. Potentially overfitting applies even in this case because it's about the fact that you have visibility to the full data, right? But I think that's more of a machine learning discussion that we could have on the side. So the question was about overfitting, which is a concept that relates to what we're doing here in terms of splitting the data into training and testing. Even if in this case it doesn't apply, it certainly will in the more complex ones. But we can still have an offline discussion about that. Any other questions or comments about this? Did this make sense to everyone? Our first recommendation engine in 2 lines? Yes? Okay, and so if I define that function, we can use the machinery that we built before, and I can use the evaluate method there. And I don't know if you noticed, this is a bit of a Python piece of functionality. Python allows you to, you can think of an object you can think of a function as an object itself. And so what this function evaluate is actually taking as a parameter or as an argument is another function, right? And so then it runs it and it puts it through the test set. So just a piece of information there for you to kind of understand what's going on. So once I define that function, it performs at 1.26. And I can't remember whether that was it worse? Is it better or worse than our baseline?
I'm getting worse for mean of this user's ratings than mean of all rating.
Sorry, say that again. I didn't quite catch that.
So it's getting more of an error if the estimate function says the mean of this user's ratings than if it just says the mean of all ratings.
Okay, but you're getting ahead of everybody else here because you're up to that's a great point. That's a bit of an evolution of another or a bit of a different baseline that we could also try out. So if I heard you correctly, you were computing the mean of the entire data set instead of just for that user. Is that correct?
Well, I just did that instead of 4, but it's probably pretty similar.
Right, right. And that's a perfectly valid solution as well. In this case, though, to stick to the content nature of this solution, we want to stick to only the ratings or the interactions that this specific user has had.
Yep.
Okay? But that's a solution that we'll want to evaluate as well. So why don't we switch over to the questions notebook, Reco systems questions, minimal Reco engine v1.0. And then what I'll ask you to do is to build the collaborative counterpart of this. So our v1.0, sorry, was the content-based recommender system that takes the average ratings of that very user. What this question is asking is, how do you build the collaborative counterpart that looks at the average ratings for that movie, but from other users? Okay, we're looking at the columns now. So I'll give you a few minutes to work through that. So how's that going? You gonna get a show of hands for people that didn't get it to work? Everybody? Okay. So can I have a volunteer to explain the solution? Someone in the back? Yeah, go ahead. Pretty much the same thing, except... Okay, so I'm just going to copy these two lines and see and work from there, okay? But this is kind of a guide here in the comments. So first we want to index into all the ratings for this movie. So how do we do that? Okay? So we want to say movie ID, okay? And change that to make it the item condition. That would be more meaningful. Great. So I got two returns here. Okay, so I'm just testing it out for a sample user and a sample movie there. I think I had a version here that actually looked at a bit of an edge case. But there's something that we missed there, isn't there? Because, so a couple things, right? First of all, we want to make sure that it is the same item, so there's a movie condition. But we also need to watch out for users that are the same as me, right? So we want two conditions. We want a user condition such that the user is not the same. And we want an item condition or a movie condition such that it is the same movie, so that we get everyone else's. And something that I wanted to point out here is that take a look at how cool this is. You can combine using this Boolean operator, this logical operator. You can combine multiple conditions into a single indexing operation, right? So I'm literally saying the user condition and the movie condition. You can see how expressive this is. And then something else I wanted to point out, another bit of an edge case here, is that it could be that the ratings by others is empty. And empty is a property of the data frame that we didn't talk about before, but it's just a Boolean property that simply tells you that, whether there's nothing in it. So there's something that we need to do if we're building a real system that always needs to output a score. Then if it happens to be that according to the way I'm computing the scores, I have nothing to go by, then I still have to fall back to something, right? And this almost starts to get into the territory of hybrid solutions, because as you can see here, a hybrid solution could also be one that falls back to something else if you don't have what you need to go by in terms of a collaborative filter, right? And so I think I heard someone say that 4 was a better idea overall. So maybe that's where a baseline informs us what to put in here, right? Or something else in terms of combining. And then this is how we evaluate that. What numbers did you get for RMSE? Anything similar to that, more or less? Okay. It actually turns out that for this set of training and test pieces, we do get quite a bit better performance using this standard collaborative filter. Okay? Very standard mean-based collaborative filter. Did everybody follow us there? Okay, so what I think we should do then, before we talk about more formulas and jump into the later versions of the Reco system, we'll just pause here. We'll take the break, I don't know if coffee break is coming or if we still have a few minutes, but we'll pause right away anyways. And then if you want, until coffee arrives, what we'll do is we'll go around and try to look at a few of the issues that you might be having. Is if it's returning an NaN, or if you didn't quite catch the two conditions or the edge cases and whatnot. Because I really want to make sure that you can write this function and you can reason about it, because what's coming is going to be more complex. Okay? Does that sound good? All right. Everyone here? Anyone missing, raise their hand. Everybody get their coffee? Yeah? Or something like that? All right. Something to wake you up. Okay, so we are at the very first round of the mini challenge. Okay, now before we get to that, before we let you go ahead and explore, this is really what, so just to kind of introduce the second half of the tutorial, really the intention here is that we dedicate most of this half, if not all of it, to you exploring new versions of the recommendation engine. And the other thing that we're going to introduce a few things, a few more concepts. It gets a bit more mathy. We're back into the theory, so from practice back again to the theory. But the idea is that that'll give you the concepts and the tools so that you can explore more other sophistications of the content-based filters and the collaborative-based filters. And from then on, once we get to the second round of the mini challenge, you guys can really start to combine as much as you want. The two of them, come up with your own hybrid setups and so on and so forth. The idea as we get there is that we'll have a leaderboard and people will be able to post their scores and we'll see them live up here. And we'll also click into your notebook and see what you've done, and we'll look at it together, right? So it'll be a bit of an interactive setup. Should be fun. So as long as you can contain the excitement, I'm going to continue with more formulas. So here's some basic ways in which we can generalize this very simple idea of mean-based algorithms that we discussed before. And I think there was a question from the back, actually, that kind of, somebody came up and said, well, what you're doing is, in the collaborative case, right? What you're doing is you're taking everybody else's rating and then you're just averaging that. Shouldn't you want to do that only for the people that are similar to me? Shouldn't you only want to consider or pay more attention to the ratings of those that are similar to me? And similar could be a number of different things. Well, that's exactly the kind of intuition that we're going to introduce here. Now, what's important to realize is that this intuition can apply to both the content case and the collaborative case. Because just like we can look at similar users to get to see what they thought about the movie, we could also, when looking at an individual user's rating history, we could also try to do some similarities across items, perhaps, right? By looking at some things that are content specific. So how do we generalize that? Possibly by incorporating metadata about items, for example, in the case of a content-based filter, right? So the idea now is that what used to be my very simple mean aggregation or average aggregation now has become a bit of a more general weighted average or weighted mean computation over the ratings in the user's history, right? And you can see that by the fact that there's a sim function here that takes two items as arguments, right? So that'll compute a number, presumably in this case, because it's a weighted average, it'll be a number between 0 and 1 that will have the semantics of a weight into this weighted sum, okay? And k is just a normalizing factor. You don't even need to worry about that too much at the moment. But basically, if that similarity function doesn't return values between 0 and 1, then we want to make sure that this is a normalized sum. And so that's why we introduced a k factor in there. But I don't think that's very important. Now, in the same way, when we generalize the aggregation functions for collaborative filters, we are going to look at similarity functions that take two users as arguments instead of two items. Right? and we're going to try to compare users in terms of perhaps their profiles. If you've filled out a profile in the system, then we could use that. If you've logged in with Facebook, maybe we could use that. All kinds of things, right? These are the additional data sets that we can look at. In this particular case, we're only going to look at the actual ratings data, but there's other ideas out there that you could explore, and that's part of the challenge. So how are we going to do this? What kind of machinery are we going to tap into from the pandas library to be able to write these similarity functions? We're going to use the aggregation framework. Okay, so pandas comes with an aggregation framework that basically is based on the very simple idea of split, apply, combine. Those of you familiar with SQL will find this very natural. Those of you familiar with MapReduce will find this very natural. The idea is that you split the data in an object according to a key, right? And then you apply a function to each of the subsets, and then you combine everything into a new object. So if you're familiar with SQL's, for example, group by, then you'll understand what we're talking about. And if not, the examples here should make that clear. So feel free to interrupt at any point with questions. We're just going to go through basically the functionality that pandas comes with to be able to do this, and then we'll jump into the solutions. So how do you use group by? It's very simple. There's a function called .groupBy, a method called groupBy, and you can call that from any data frame object. And so in this case, for example, look at how powerful this is. If I wanted to know the average ratings by gender, then this one-liner will give me that out of my data. And you can go ahead and try that if you want in the questions notebook. If you group by gender, group by anything else actually, try it out. Or group by many things, in fact. If you can see here, you can group by both gender and age. And then you can select out of that grouped object what it is that you're interested in exploring. So in this case, for the most part, we're going to be interested in the ratings column. And so we're going to index into that, and then we're going to aggregate it in some sort of way. In this case, we're using an average, right? And so here's the representation. You can get an average rating by gender, and you can get an average rating also broken down by age. And I think age in this case is just a set of intervals that this data comes with. It's broken up into these age brackets, so to speak. Any questions about that? Fairly simple. I'm going through the main notebook, but I encourage you to try it out if you want in the questions notebook. And the only reason I say try it out in the questions notebook is because the question notebook explicitly loads the train and test CSVs. And so that way we all get comparable results. Otherwise, in the main notebook, there's no loading of that. Okay. Pivoting is another important concept, another built-in method of the pandas data frame that allows you to do all kinds of transformations of a data frame. We're going to start with an example of just a rearranging of columns and rows, and then we're going to see how pivoting can also be a bit of an interface or syntactic sugar, if you will, depending on what your taste is, into the group by framework as well. So you'll see a connection there. So first of all, suppose that we take the movie lens train data frame, this spreadsheet that contains all of the rating events. How would we obtain a ratings matrix out of that? So the original matrix that I showed you at the very beginning of the tutorial when we were talking about the definition of the problem, of the recommendation problem, the data that we have is not in that format. How can we reshape it so that it looks like an actual matrix? Well, pivoting allows you to do that. There's a pivot table method that's built into the data frame object. And you can say which values you want as the body or the cells of your matrix, and what you want the index and the columns to be. So very simply here, by passing in those 3 keyword arguments, I immediately obtain a ratings matrix with users along the rows and movies along the columns, right? Now you can see the reason I'm doing this only is both so that you can see 2 reasons. One, so that you can see the power of pivot table and what's one of the things it allows you to do, but also so that you can very clearly see how those question marks that we had at the very beginning are very real. This is the real data right here. You can see that most of the cells in there are non-existing right? They're empty. There's no numbers in there. So that shows you the sparsity or the sparse nature of the data that you usually have to deal with in systems like this one. And so what I'm doing here is using the lock indexer to try to show you that indeed not everything is empty. There's a few numbers in there, and so I spent a few minutes randomly scanning the very large matrix to show you just a number in there hidden amongst the NANs, right? So that really puts the sparsity challenge very, very front and center. Now, as I was saying before, the more interesting case with pivot table is using it as an interface to group by. So remember what we did before. We were looking at the mean ratings grouped by or organized by gender and age. You could do the same thing with pivot table, whereby you say, I'm interested in computing some sort of aggregation over the rating values, and I want the index to be the age and the columns to be the gender, and the function that I want to aggregate with is the mean. And what's cool about pandas is that, or this pivot table functionality, is that the aggregation function could be any function. You could write your own, right? And that's where we can get creative as we build new solutions, right? In this case, if you pass the string mean, it'll just use the standard and built-in mean. But if not, you can pass in a function of your own. In fact, you can pass in a list of functions, right? This call, I'm just going to zoom out so that you can see. This call is exactly the same as the one before. I'm just the only difference is that I'm passing in an actual list of functions. And that didn't really work. Okay, there we go. And I'm using NumPy, the NumPy mean function, and the NumPy standard deviation function. And Pandas is smart enough to even use the names of the functions as a hierarchical index here to display the data frame for you. Don't worry too much about the hierarchical indices. In this case, that's what it's using for the columns. All you need to know is that you can get it gives you a way to differentiate between the two F columns that you have here and the two M columns that you have. One of them is for the mean, and the other one's for the standard deviation. So you could think of this as kind of like, what is the average rating for that group of age and gender, and what is kind of like the disagreement, if you will, of that group in terms of ratings, right? You could think of that as, of this descriptive stat as that, having those semantics. Yes, you can. Yes. So the question was a very good question. The question was, can you use a custom function in the group by? Yes, you can.
So just to check the understanding, a couple calls back.
Yes.
The first pivot table, whereas that one there. So that's the same thing as doing group by.
100%. Yes. That's why we were saying that pivot table can be thought of as an interface to group by. You might find that this syntax is a bit more succinct. And more easy to understand, more easy to work with. This is what we're going to use for our recommendation engines coming up right now. Any other questions or comments? Okay. So now that we've covered that theory and we've covered the pandas group by functionality, we're ready to use that machinery into and to apply it into a bit of an enhancement or a more sophisticated version of a record engine. We're going to call it V11. And so as preparation, one of the things we're going to need is a user index from the user's portion of the data set. And that'll allow us to retrieve information, personal information about a given user in a more convenient way. So I'm just going to call that user info, and it'll be the original users file that we loaded using PD read table or read CSV. And I'm going to set the index to user ID. So this is just a data frame that looks like this. And the only reason why we're doing this is so that, for example, if I had user ID number 3 and I wanted to know their gender, then this allows me to do that very quickly. I have a function or a method that allows me to quickly retrieve that. And I'll show you how we're going to use that here. So we're going to write a collaborative-based filter using an implicit similarity function. And by implicit, I mean we're going to have a similarity function that instead of doing some sort of weighted average across the ratings of users. The average is going to be, the weights are going to be hard ones or zeros. It's going to be a step function, so to speak. And what we're going to do is we're going to completely ignore ratings from other users outside a particular interest group, so to speak. So, for example, if you want to guess what I would think about a particular movie, then you're only going to look at people with my same age, for example, or my same occupation, or my same gender, or whatever, right? That's an implicit similarity function. I'm assigning a 1 to the ratings by users in the group and a 0 to everybody else. So how do we do that? We can define this function called collaborative by gender. It's, again, the same signature, user and movie, okay? And we're going to use the same few lines from the previous collaborative filter, the same conditions. We're going to need a user condition, a movie condition. We're going to get the ratings by the others, and if it's empty, we have a fallback, okay? Now, once I have all the ratings by the other people, what I want to do is only look at those in the same interest group. And in this case, this is by gender. So what I'm going to do is I'm going to take those ratings by others, put it through the pivot table process, and it'll come back with a means by gender data frame. Okay, everybody with me so far? What I'm going to do with that is, using the user info data frame that we prepared before, I'm going to get the gender, or whatever piece of interest it is that we're looking at, for the user in question, for the user that's passed into this function. And then I'm going to use that to index into the means by gender. So for example, if I pass in here user ID 3 and it's an M for gender, then what I'll do is I'll index using that information into here, and I'll return the mean, sorry, in this case, I'll return the mean based out of that interest group. Now, there's a few edge cases to consider. That's why you have the if statement there. It could be that in the interest group, I'm the only one in that bracket, or I'm the only one in that gender, or I'm the only one with that occupation or zip code. So if that were to happen, I need a fallback. And this is where the fallback mechanisms can get very creative. Okay? And so if I put that through the evaluator, it comes back with a 1.19 RMSE. Okay? And if I recall, if I remember correctly, I think this is slightly worse than our standard collaborative filter. Isn't that right? Don't remember? Is it? 15, right? So slightly worse. In this case, and it should be the same for you if you're using the same training and testing data sets, and that's the purpose of that, so that we all agree. So maybe we could discuss about why that's the case, but beyond that, with setting the interest on trying other ideas and learning about pandas aggregation, what we're going to do is try to get you to write a few variations of this. So before we do that, I just want to make a comment that I don't know if you realize, but this is going to be a little inefficient, this function. And the reason for that is that the means by gender data frame is not necessarily going to change very much, right? We're kind of redoing that all the time for every estimation that we receive into this function. So it seems that at this point, and you'll see that in the literature as well, it seems that at this point it seems worthwhile to write a learn function to pre-compute whatever data structures we need at the point of estimation, at the point that we want to make a guess, right? And so we can graduate our single function recommendation engine into a class. That's amazing. And we can split up the work into learn and estimate. And the gist of that is that you only call learn once with some data, according to the data that's passed in or the data that you're working with for training, and then you can use that trained model to evaluate on different users and movies, okay? And this works just in the same way. So if you define this class with the learn and estimate method, then you can instantiate that. You can call learn first. So you call learn offline, so to speak. And then you can pass reco.estimate, which is the function that we want to evaluate, into the evaluation framework. Okay? And you can see that it is exactly the same performance because nothing has changed. I'm only just making it a bit more efficient when I call this multiple times. Okay? So 1.1953 is the same number down here, so on and so forth. Any questions about that? Cool. So what we'll do now is we'll go ahead to the first round of the challenge. And what I want to show you is how to, I want to show you a couple things so that we can have the leaderboard up. So just a few notes. This is not a real challenge, so play fairly. Focus on understanding the different versions of our minimal recommendation engine. Try to mix and match some of the ideas and then evaluate and post to the leaderboard. I just want to mention that if there's a function that I'm going to show you now, I'll show it to you right away, that in order for you, so here's what I suggest. The people that are on the hosted setup, you can go to the questions notebook. Okay, you can go to the questions notebook here. Go to the first round of the challenge. Well, you see some directions on some suggestions about what to do. So try out a collaborative filter using age similarities, using zip code similarities, occupation. If you do a content-based using movie genres, that's one that's a bit more challenging. You have to massage the data a bit more. Then you can have a look at that. We'll give you some time and we'll go around and help you out. You can do that on the questions notebook, and you can test it using evaluate in the same way that we've been doing that. If you're on your local setup, you can do the exact same thing. Try out a few iterations, pass it through evaluate, until you get to a number that you think is good, that you're proud of, and you want to share with everybody else. You want to share the performance of your Reco engine. When you're ready to do that, the people that are on the local setup, I'll ask you to actually go to this website, pycon.unata.com, after you're happy with your score, pycon.unata.com, and enter a username in there, pretending that you're going to use the fully blown hosted setup, but you're not going to. You're just only going to open up the questions notebook. And what you can do is copy paste your function or your class into the questions notebook. You can even create a new notebook if you want, standalone just for that. And there's a built-in update score module in the hosted setup that you can import. And you can call this function update score using evaluate of my function. And the reason why I was saying before, so here's what this would allow us to do. Once you do that, I'm going to go into the leaderboard, and you'll see that for as long as you have an account there, your name will show up, but until you post, the score will show up as none. I don't know if you can see that. That's the number of people that we have there. So I'll give you an example. I'm going to go to, so this is pycon.unata.com. I'm just going to go to questions. Okay. And then I'll go down here, and suppose that, and this is something that I didn't want to give away, but I'll suppose that my score was a 0. I'm gonna post that score. Do I have a typo there? No. Okay, let me do that again. So here's how it should work. Okay, so pycon.unata.com, questions. Oh, this part might be failing. Okay, we'll fix this very quickly, but the point is that your score will show up on the leaderboard, and we'll have a running tally of how you guys are doing. So I'll let you guys go to the questions notebook and work on a few variations of that, and then we'll fix this little problem here. Okay? having gone through these ideas over here for the first round of the mini challenge. Can anyone tell me if any of these are, let's leave the last one out for now, that's a bit more complicated, but can people tell me if age or zip code or occupation were particularly useful? Did they perform better, worse? Are we still better off you looking at everybody? Any comments based on the results that you got? Fairly similar? In your case, age seemed to work well? Okay. Zip seemed to work the best? Okay. So you know what? We're going to try something because the leaderboard for some reason isn't quite posting. So if you don't mind me looking at the solution that you wrote, is that okay to show to everybody? Oh. That's fine. Which one is your, you didn't post lead. Okay. What is your username? Sorry? MUTLU. Okay. So I just wanted everyone to see the solution. Was it in the questions notebook? Okay. Okay. Just wanted to see the actual performance that you got out of it. So here's the first round. 125. So does anyone remember how that stacked against that baseline that we started with? Just simply returning 3 or 4 or whatever? Okay, so slightly better if not the same. Okay. Okay. All right, so what I wanted to do before we start looking into combining these or talking about why it might be that this worked or not, just to make sure that we introduce the last set of concepts in the tutorial, and then we can leave you, or we can all sort of freely discuss other ideas. I wanted to take you through the last version or the last iteration where instead of using the concept of implicit similarity functions, we're actually writing our own custom similarity functions. And I think this came up in a discussion back there as it relates to the suggestion here for the first round, which is building a content filter based on movie genre. Okay, so if you want to take a stab at that problem, you're going to need to write a custom similarity function of your own to deal with how do you compare two movies based on the genre. You need a number coming out of that. You need a similarity function. But more generally, that can apply to users as well. So we'll leave the second round here just for a moment and go back to the main notebook. And I'm just going to introduce a few ideas for our v1.2 using custom similarity functions. Okay, and I'll show you how you can use the pandas machinery and NumPy to create functions of your own that you can pass into here. And we'll see how well how well we fare in terms of performance. And then we'll go back to the second round or pick up where we left off from the first round if you so prefer, because I think we're doing pretty good on time. Does that sound good? Okay, cool. So a few similarity functions that I want to introduce. And again, this is a bit of a very broad topic as well. We're only going to talk about 2 or 3 functions here, just so that you get a feel for what they look like in Python, how you write them, and also with an eye on making sure that these functions operate on pandas not data frames, pandas series, because that's essentially the inputs that we're going to receive. So again, these were all written to operate like that on 2 pandas series, and each one represents the rating history of 2 different users. So we're going to focus on similarity functions that measure similarity between 2 users. This concept we will then have to apply to items if we want to do content filters for things like the title of the movie, the year, or maybe even the genre, because genre is a set or a list in the case of our data set. So you can apply them to any 2 feature vectors that describes users or items. In all cases, the higher the return value, the more similar the 2 series are. You might need to add checks for edge cases, such as divisions by 0 and things like that. So if you get errors like that, then you might want to look for those edge cases. So we're going to start with Euclidean similarity. You might have heard of this one. This is what it looks like. It's kind of like a geometric similarity, but it's inspired by the geometric similarity, but there's a 1 plus there to handle that edge case, and it's the inverse of that, so that the higher, the more similar. Again, you don't really need to worry about the math. I think looking at what it is on NumPy and pandas is the intent here. So this will take 2 series objects and return the Euclidean similarity. Cosine similarity is this function here. So you have the dot product divided by, this is the modular really, because you're doing dot product with yourself. And then square root of that. This is what it looks like using NumPy. So again, these are all one-liners. And finally, the Pearson correlation. Actually, there's a few more. Pearson correlation is this function here. You will find that this is a bit of a popular choice when you want to compare 2 rating histories. It has a few interesting properties that I encourage you to look at. Especially, one of the cool things about, you can even do this on the notebook, and I encourage everyone to do this on their own. Take these similarity functions and then apply them to, try to see if you can plot their behavior for various kinds of inputs. Actually, if you go to the Wikipedia for various similarity functions, you'll see what the plot looks like and how it behaves depending on the scale and the nature of the inputs that you're working with. So you'll get a feel for the behavior and what kind of robustness the similarity function will afford you. Jacquard similarity, also a popular choice if you're thinking about elements in a set. Then Jacquard is kind of like looking at the size of the intersection over the unions, right? And there's a binary version here in case your elements or your values in your series are only 0s and 1s, okay? So what we're going to do is, again, these are all, think of these as all functions that you can drop in to what we're going to build now to try different ideas. So what we're going to do is we're going to take Pearson correlation and we're going to build a collaborative filter using that custom similarity function. So the idea is that we're going to aggregate over the ratings of everybody else for the same movie in order to obtain a recommendation for a particular user. But that aggregation is going to be weighted. And the weighting is going to be determined by the Pearson correlation similarity between the user for whom we want to estimate the rating and all the other ratings by the other users. Okay, so what we're going to do is we're going to, for example, if we're estimating for myself, I'm going to take my ratings history and I'm going to compare it with everybody else's ratings history using the Pearson similarity. And that'll kind of give me an idea for, am I a critical rater, like we were saying before? Am I a very critical harsh user, harsh rater, or not? Do I tend to give everything a 4 and a 5, for example? And so that way, there's a way to do away with that. There's a way to normalize that, right, to avoid that problem or that skewness, and then obtain a similarity coefficient between myself and everybody else. And that's how we'll kind of pay attention to the opinions of those other users when we are rating for anybody. That's kind of the English explanation of what this math is going to do for us. Any questions about that? Does that more or less intuitively make sense? So again, we're going to use a little class so that we split the work between learn and estimate. And the real interesting part here is in the estimate function. So it's really, it's no more than a handful of lines, but what we're making use of here, the new machinery from pandas, is the apply function that you'll see right there. So here's what happens. It's the same setup that we did for any other collaborative filter. We're going to take the ratings by everybody else for the same movie. We're going to apply that condition. We're going to make sure that if it's empty, we fall back to something. If that's not the case, then what I'm going to do is I'm going to obtain the ratings by the other users and the other users' IDs. And then I'm going to use the matrix, the ratings matrix that we built before in order to access the user profiles. So I'm using the term user profile here only to mean a series object that contains on the index the movie IDs and on the values the ratings. So if I look at your profile, then I'm going to have an index of the 10, 15, or 30 movies that you've seen. And for each one, I'm going to have a rating. If I'm looking at somebody else's, it'll be a different length and different movie IDs. Okay, that's the profile. So I'm going to, from ratings by others, I need to do a set index operation so that I can then use the user IDs in here into the indexing. I'm going to obtain their ratings and their profiles, and I'm using there for everybody else, and then the user profile for the profile of the user in question, which is the one that's passed into the function here. And then what I'm going to do is I'm going to apply, I'm going to use the apply mechanism in Pandas. So if I have a Pandas data frame, and there's a function that I want to run on each of the rows or on each of the columns, which is this case, I have my profile, and I have a data frame of everybody else's profile. And what I want to do is I want to take that profile and match it individually to each one of them. Then apply is the kind of method that you want to use. Apply will allow you to select whether you want to compute along the rows or whether you want to compute along the columns. So you pass in a function. In this case, I'm using a lambda function. It could have been something that we define somewhere else in the code. And I'm simply saying calculate the Pearson correlation between my profile and the profile of the other user. Okay? And once I obtain that, which I store in a series called similarities or sims, I am simply going to, provided that there's no weird edge cases, what I'm going to do is I'm going to return the average of the ratings, but the weights that I'm going to use are the similarity scores that come back from that application, right? So notice how before we were doing np mean or dot mean to return just the average for everybody. Now we're using np average, which is a different function in NumPy. It's a different top level function that takes a keyword argument for weights. And so that allows me to do a weighted average of the ratings. Okay? And luckily, what we spent the most time and our most amount of effort on in terms of building collaborative filters and the different versions happens to be the most successful one so far, right? So this idea of paying attention to those that rate similarly actually pays off. Look at how low that RMSE is. It's low for us compared to everything else we've seen, right? So any questions about this? Did this make sense for everybody? So again, the second round is about exploring with other similarity functions. It's about using this idea but applied on the content level as well. But if you feel that you want to go back to the first round and pick up where you left off, then we'll give you time for that. From now on, that's what we're going to do. And what I'd like to see is if somebody comes up with an interesting RMSE that is close to this or better or whatever, then we'll do the same thing we did with somebody back there just before. We'll put the notebook up for everybody to see, and we'll discuss that solution. Okay? Okay, cool. So we'll give you guys time to do that. So the leaderboard, well, it seems to be showing some scores, but I don't really trust it. So I would rather ask if anybody, if there's anybody that had an interesting score that they wanted to share so that we could put up the solution. Something close to that one, I think it was 112 that, sorry? Okay, so what is the username that you used here? SF right here? Okay. So let's take a look.
A little better than that one.
Okay.
It's way slower and always slightly better.
Okay. Where is it? At the bottom here?
At the bottom of the question.
And the number that you the performance that you were getting. Oh, okay. I see. Is this the latest refresh? Because I see that type error here. Okay, so I'll close here and reload. Let me know when. Okay, let's see. Okay, cool. Oh, wow, 105. Great. So walk us through it.
So the similarity is pretty much the same as the solution there, but I mixed in a measure of the users, which is just binary similarity. It's the same thing I used in my solution above. So the solution above this one is actually probably more interesting because it's less exactly the same as.
Okay, let's go through that one first then. What, is it up here?
Yes.
Okay.
It's in that one.
Okay.
So that's like
Oh, I
a
see.
mixture of the mean of the ratings for that movie and mean of the ratings for similar users, but similar in this case is just binary, same gender, same occupation, and within 10 years of age.
Cool.
Most of the complexity is in, I did it as like a list of tuples of weights and measures so that I could adjust the weights more easily.
Nice. So how did you get to 0.6 and 0.4? Just trying out, just basically trying it out?
Trying out random things.
Cool. So does everyone understand the basic idea here? This is a classic example of a hybrid, right? We are combining scores from different techniques using a linear combination, which is this weighted average, right? And you can learn those weights. You can try them out. Learning them like that is perfectly legitimate. There's also automated ways to do that. But this is a perfect example of a hybrid that is actually combining collaborative and, in both cases, it's a collaborative combination, right?
Yeah.
Yes.
So and then in the second case, I'm just replacing the first line of that with the example, which is instead of ratings for the mean of ratings for this movie, it's the mean of ratings for this movie weighted toward users rated similarly.
Based on Pearson. Great.
I did try out a similar.
Okay, well, I think that warrants a big hand for the best solution. That's a very creative one. Actually, I actually think that this is the best one we've seen in the series of tutorials, because we've seen other linear combinations like this one, but I think this is performing the best. So thanks for that. That's great. Anybody else that care to share or want to make a comment or question about this or anything? Okay, so we're gonna stick around. So if you have more questions, if you want to ask us about other ideas, we'll be here for a few more minutes. Other than that, I just want to thank everyone for your patience and for having chosen the tutorial. It was a real pleasure. So thanks.